from minus 90 or minus 70 up to about a minus 60. And since you are closer to the threshold, any small stimulus is going to trigger. In other words, you're going to get hyperexcitability. You understand? Can somebody tell me why, and this is very important, why in hyperkalemia the resting membrane potential moves closer to the threshold? Or why in hyperkalemia, okay, the resting membrane potential becomes less negative? Yes, sir.
More potassium ions are diffused into the intracellular fluid.
But the potassium, no, don't make a noise. Listen carefully. My repose to that is this. I have a higher potassium on the inside than outside. So even though I'm having hyperkalemia, why will the potassium go in?
Outside, sorry.
Now you're telling me it's going to go outside. Yes, sir.
Sodium in the cell, but the potassium leaves. This what makes it more positive.
Yes, sir.
Because the resting membrane will change to the cell and also for the potassium.
Sorry, the resting membrane will change, yeah?
For the cell and for the potassium as well.
What you mean is the resting membrane is becoming less negative, but the nursed potential for potassium is also changing.
No,
Remember the nurse, the Ci over Co?
Yeah.
That's also changing because I'm changing the concentration. But why is the resting membrane becoming less negative? Yes, sir.
Since the concentration inside is higher, it's going outside due to the difference in concentration.
Yeah, but I'm making the outside higher. Hyperkalemia means making the outside higher.
Yeah, basically, because the potassium is going from inside to outside,
Yeah?
that makes the outside higher than inside.
No. Remember, understand something. All of you who are thinking and putting your hand up, understand something. I really do not require too many ions to move back and forth. So when you tell me it's getting higher outside than inside, that means the outside is going to become like 152 and the inside is 142. That's not the case. I'm only going from 4 to 7. Okay? And that's not 152. Yes, sir. Last contribution. Yes, sir.
I think it has to do with the charges. Like the positive charge outside is much greater now, so it's attracting the negative.
What's your name?
Basel.
Huh?
Basel.
B-A-S-E-L.
Yes.
Basel. Basel, answer this question for me. And this has nothing to do with what I asked you. Okay? Answer this question, Basel. Which ion is mostly responsible for the resting membrane potential?
Chlorine.
Potassium.
Because the channels are open at the resting.
No. Follow my logic. Which ion is mostly responsible for the resting membrane potential? Yes? Potassium. Why is potassium mostly responsible for the resting membrane potential?
Because it's the most effective one.
Because potassium is leaking out through the potassium leaky channels. There are other kinds of potassium channels in the membrane, but potassium, we're not bothered about those. We'll bother about them now. Are you with me? But the leaky potassium channels are allowing the potassium to leak from inside to outside. Why is it leaking from inside to outside?
Concentration.
Because of the concentration gradient. Now, if I increase the outside a little bit, will the leakiness of the potassium be greater or lesser? Lesser. That means the potassium will do what? Will stay in the cell. What charge is the potassium? And if it stays in the cell as a positive charge, what happens to the resting membrane potential? It becomes less negative or more positive. Okay? And obviously the opposite will apply when you have hypokalemia. Okay? In other words, the potassium will go out quicker, thereby making the inside of the cell more negative. Hyperpolarization. Okay, let's come back. So, changes in the membrane potential. So we had a resting membrane potential of about -70, -90, and we want to change it. We want to make it less or more negative. If you have changes in the membrane potential, they take place when the concentration of the ions across the membrane will change, like the potassium. And at resting membrane, the most important ion is potassium. Again, permeability of the membrane to the ions will change. So if at resting membrane potential, I change the sodium channel, say, now I'm going to affect the membrane. Okay, the voltage gated sodium channel. If that change, all right, switches, in other words, the resting membrane potential becomes less negative or more negative. There's a name for it. I'm moving away from the resting, either going upwards or I'm coming downwards. I'm not talking about action potential yet. All right? These small changes, a little bit upwards or a little bit downwards, are called graded potentials. They are not action potentials. They will not go down the nerve. They might stay near someplace on the nerve. You understand? Now, how do I make a graded potential into an action potential? I need to exceed what? Thank you, the threshold. I need to exceed the threshold. That's when a graded potential becomes an action potential. So a graded potential is important because I can have 2 or 3 graded potentials. Okay? And if I add all of them up, I might get an action potential. Or I might have 2 positive graded potentials and 1 negative one. In other words, 2 are making the potential to go up, 1 is making it to go down. And when I add all of them up, I end up with a summated graded potential. In other words, I can integrate the information. You understand what's happening here? So, graded potential. Action potentials are obviously when you go past the threshold and then you come back down to normal. So, look, depolarizations are small upward movement of the resting membrane potential. Remember, the threshold is up here somewhere, so this is not an action potential.
Great.
Okay? So anytime you have a small going up, that means it's a depolarization. In other words, a reduction of the membrane potential, resting membrane potential, in the direction towards 0. Not reaching 0. Okay? Again, inside of the membrane becomes less negative, increase in permeability will produce this kind of thing. On the other hand, if I move it down, all right, like in hypokalemia, then that is called a hyperpolarization. A hyperpolarization. So how do I hyperpolarize a membrane? I can either change the potassium concentration on the outside, or I can open up a chloride channel. Why will opening up a chloride channel hyperpolarize a membrane? Yes, sir?
If chloride ions go inside, chloride is negative, so it's going to make the inside more negative.
Alhamdulillah, good. Okay, and that is what happens, all right, with a neurotransmitter called GABA, gamma-aminobutyric acid. It opens up chloride channel, okay, and then chloride goes in. Glycine, you heard of glycine?
Yes.
An amino acid, glycine, is actually an inhibitory neurotransmitter that opens up chloride channel, okay, in the spinal cord and the brainstem. So anything that's going down will be a hyperpolarization. I'm just giving you 2 basic definitions of the voltage movement away from the resting membrane potential. Okay, fine. Now, so there's that. Can you see resting membrane minus 90? Are we okay? So any upward movement will be called depolarization. Any downward movement will be called hyperpolarization. Now, if the depolarization is great enough, so that by great enough I mean about 20 millivolts. In other words, greater than threshold. Can you see threshold?
Yeah.
All right? Then the depolarization will go all the way past threshold, and the minute you reach threshold, now you cannot pull it back. In this case, you can pull the depolarization back. Once you reach the threshold, you can't pull it back. That's why it's called all or none. The action potential will be all or none. Then you will get an action potential going all the way up to 0, and then you get an overshoot. Any voltage above 0 is called an overshoot. But it's all depolarization. From here to there, from there to there, from there to there. Now when you come back from this top part down, that's called repolarization. Okay? It's called repolarization. So have a look now. So now we're going to look at the action potential. Remember we looked at the resting membrane potential yesterday. Now we're going to look at the action potential. This change in excitable tissue. So depolarization is any voltage that makes the resting membrane potential less negative. Are we okay with that? Yes. Good. All right. Repolarization is any membrane potential that makes the membrane more negative. It could be from positive all the way to negative, or it could be from negative to more negative. All right? And repolarization will be from positive all the way down to minus 90. Hyper will be from minus 90 to minus 96. You follow?
Yes.
Good. All right? Now, remember, in membrane neurophysiology, which you are studying now, a current is not an electron like you studied in physics in high school. A current, for us, is the movement of an ion. Sodium ion, potassium ion, chloride ion. So the inward flow or inward current would be the movement of an ion. Okay? So an inward current flow will be a positive charge that's moving inside. In other words, it depolarizes the membrane. Because the membrane is negative, if a positive charge comes in, it depolarizes. It makes the inside less negative. So we call that a depolarizer. An outward current. Again, because potassium is high inside, the movement of a potassium outward will make the inside of a cell more negative. Therefore, it will hyperpolarize a membrane. What is an action potential? Again, of nerves, muscles, and endocrine cells, where you depolarize, reach threshold, you then go all the way up to the top to 0, above 0, and then you repolarize all the way back again. And that would be A. So, depolarization rapid, upstroke, then a repolarization, that would be an action potential. The graph is coming on the next page. Okay, now, an action potential is the same size and the same shape all the time. You do not have a small action potential or a big action potential. Therefore, it must have a stereotypical size and shape, and it can move. In other words, if it starts at this end of the axon, it will move to that end of the axon. You follow? And that I will talk about how it moves tomorrow. Conduction is tomorrow. Now, once it starts, what do I mean by once it starts? The action potential.
After
Once you reach, the small depolarization reaches threshold. You cannot stop it. It's all or none. It either takes place, that means it's above the threshold, or it is below the threshold and doesn't take place. The threshold is when sufficient numbers of voltage-gated sodium channels will open and allow the depolarization to go beyond the -50 all the way up to 0, then plus 40-ish. Okay? So that would be the threshold. In other words, you got sufficient voltage to open up enough voltage-gated sodium channels to allow the current to flow through the nerve. Okay? Now, there's the diagram. So there's resting membrane potential. Number one, resting membrane, due mostly to which ion? Yes, Baza?
Potassium.
Thank you. Okay, the potassium ion. Now you have a slight depolarization. There's your slight depolarization. Can you see two? Can you see two?
Yes.
All right, a slight depolarization. All right? Now, that depolarization can be because a little bit of sodium is coming in. Why is the sodium coming in? Maybe a sensory receptor has been triggered. Somebody's poking me or something. Okay? Now, as you get the depolarization, it goes up. But as it's going up, it must reach the threshold. And again, 3, it reaches the threshold. And at the threshold, sufficient numbers of voltage-gated sodium channels begin to open. Now, when they open, sodium goes from outside to rapidly, changing the inside of the cell from negative to less negative, less negative, less negative, all the way up to 0, and then even making it a little bit positive. Why is that happening? Because when you open that sodium channel, the voltage-gated sodium channel, the driving force for sodium was so great, 135 millivolts, that the sodium went from outside to inside. Okay? In other words, the sodium is trying to drive the resting membrane potential towards Muaz, its equilibrium potential. Only because that sodium channel opened. But it doesn't even reach there. Why? Because the inactivation gate senses that change in the voltage. And the inactivation gate shuts the sodium channel off at plus 40-ish. Or 30. Okay? Now, when that sodium channel is shut off, in other words, it is inactivated. Here, the sodium channel was activated. It then becomes inactivated up at number 5. See? All right? 2 things happen. The potassium channel, or the slow potassium channels will open. The voltage-gated or the slow voltage-gated potassium channels will open. They open slowly. They take their time. Okay? Now, the effect of shutting the sodium channel and opening up the slow potassium channel, all right? What happens now? What have I done to the driving force for potassium? I've increased it.
Yeah.
I'm gone all the way to plus 40. The potassium equilibrium potential is minus 94. That means I got a driving force for potassium of almost 120. And which way does potassium start to move now? Out. And now we start going out, out, out. There, pK means permeability to potassium starts to increase. It keeps going out. As it keeps going out, you then come to the threshold, and then it keeps going out, the potassium.
Till it.
And it comes to the resting membrane potential, and it keeps going out. Because it was slow to open and it is also slow to close. Therefore, it keeps going up. So that you even reach resting membrane potential, and it's now kind of starting to close. The potassium keeps leaving, you then become hyperpolarized. Okay? When you reach hyperpolarized, or you're almost nearing the potassium equilibrium potential of minus 94, now the potassium channel shuts down, decreasing the potassium permeability. Okay? And when that happens, all right, now you need to bring it back to resting membrane of minus 90. Okay? You need to bring this minus 94-ish or something back to, at least in my diagram, minus 80 something or the other. All right? You need to bring it back. And what is working at this stage is the sodium-potassium pump. Okay? And again, cell returns to resting membrane, and resting membrane potential is restored with the sodium-potassium pump. So, before I take a question, I wrote all of that for you in words. So the first part, resting membrane, you know. Potassium, yes? Good. Okay, high conductance to potassium. At rest, the voltage-gated sodium channels are closed. Therefore, sodium conductance is zilch. Right? Now, upstroke. So you're going up first, depolarization. All right? So an inward current, either a movement of a sodium ion into the cell, okay, will slowly move the resting membrane towards the threshold. Depolarization at the threshold will cause the voltage-gated sodium channels, VG means voltage-gated, sodium channels to open rapidly. When they open, sodium comes in. Sodium conductance increases. Remember, I want to go to the sodium equilibrium potential Moaz. Okay? And therefore, I have an inward sodium current. So I'm now going from minus 55 all the way to 0 up to plus 40. That's the inward current. Now, there are certain drugs that can inhibit the sodium channel. For example, this thing called tetrodotoxin. It attaches on the outside, the extracellular part of the channel. Okay? Obviously, if it attaches on the outside, then sodium will not come in. All right? That means it has an effect on the going up part of the action potential, the upstroke. All right? Another kind of drug is called lidocaine, which is a local anesthetic. It attaches on the inside of the sodium channel. Lidocaine at low concentrations, will decrease the rate at which you have the upstroke. Lidocaine at high concentrations will stop the upstroke or the depolarization. Okay? That's why it's used as an anesthetic. Other kinds of drugs that will block the sodium channel: local anesthetics, lidocaine, anti-arrhythmic drugs. These are the ones that are used for people who do not have a normal sinus rhythm. What do I mean by normal sinus rhythm? Yeah, normal heart rate. In other words, it's too high, it's too fast. Okay? And you can use class 1 anti-arrhythmic drugs. Anticonvalescent, convulsants. These are drugs that are used in epilepsy. Okay? So you decrease the sodium channel activation and thereby decrease the effect of excitation of the brain. And names phenytoin and carbamazine. So let's move on to, we looked at this part and that part. Now, as I'm going to the top, what's happening? The sodium channel starts to close, or the inactivation gate of the sodium channel closes. So there we are. Depolarization will close the inactivation gate of the sodium channel. It will also open up the voltage gated potassium channel. But the potassium channel is slow to open. Okay? So the outward current of the potassium takes place slowly. Alright? And now as the potassium leaves, it's a positive ion or a positive current leaving. That means the inside is becoming more and more negative. I bring my membrane potential back down towards resting membrane. But I have an overshoot again. I come to zero, I go to the resting, and then I have an overshoot, which is a hyperpolarization. Why? Because the potassium channel is slow to close. Again, are there drugs that will block the potassium channel? Yes. These are, again, anti-arrhythmic drugs. If you block the potassium channel, that means you make repolarization longer. If you make repolarization longer, the time, that means the heart will not beat so fast. Okay? And therefore, you can use them as anti-arrhythmic drugs. And example, amiodarone. Okay? Next one. Put it all together now. Before I explain to you, any dot, can you see the dot, the what do you call this thing? Star, whatever, represents a voltage gated channel. So start down here. Alright? At this level, only the leaky potassium channels are working. Here. So I got resting membrane. Are we okay? Good. I have a stimulus. What does a stimulus do? It opens up maybe one sodium channel. Can you see that? Maybe one. That maybe one channel will move the voltage from here upwards. Now, I don't know if that is enough. Let's assume it is enough. It takes that voltage all the way up to the threshold. Okay? Now what happens? Now all of them open. Notice? They're all open. But the voltage-gated potassium channel is shut down. Okay? So, I now open. As I open, I get depolarization up to the top. When I get to the top, the voltage-gated sodium channel is inactivated. All right? Now what happens? I open up, my friend, the potassium channel. And now potassium goes from inside to out, and then you come back down. That's repolarization. Again, the potassium channel remains open until the bottom. And then it shuts down. It shuts down almost near the potassium equilibrium potential. It shuts down. All right? And now what happens? There. The sodium channel, there are two things happening here on this side. There are two things happening. One is that the sodium channel is shut down. Remember that? It's shut down up on the top here. All right? The potassium is leaking out. But something else is happening to the sodium channel as I come down here. Can somebody tell me what?
It starts.
The sodium channel. The sodium. Yes, sir?
It's slightly open to make it at the resting membrane potential.
Yes, sir.
The activation gate open.
Good. I'm going from inactivation to a closed state. In other words, the ball is coming away and the voltage sensor is now coming back in place. That's what's happening to the sodium channel here. So that I can reopen when I get back here. Okay? So, there we go. What are the ion channels involved in this action potential? Sodium makes sense. Okay? The sodium channel at resting membrane is pretty much 0, minus 70 to minus 50. But the minute I open it and go up to threshold, sodium conductance can go up from 500 to 5,000 fold. Okay? Then, inactivation gate of the sodium channel. Again at plus 40. But what I put in red, can you see? An important characteristic of the sodium inactivation gate is that it will not reopen again until I reach. So as I'm coming down towards, on the repolarization side, as I'm coming down, the inactivation, the ball is coming away, and the little black line is going back to close the channel. I need that. Okay? I need that. Because you can only reopen the sodium channel if you have that up. You cannot reopen the sodium channel if the inactivation gate is shut. What about the voltage-gated potassium channels? Again, at resting membrane, the voltage-gated ones are shut, but the leaky ones are working. That's why I have resting membrane. As the membrane potential changes from minus 90 to 0, the voltage-gated potassium channels start to open slowly. They only open maximally at plus 40. Okay? And again, they remain open for almost 1/10,000 of a second, and that is enough to cause repolarization. So, have a look at each one of them in turn. Now, look up here. Can you see the dotted red line? Yes? That is the action potential. And you use this scale. So I'm going from about minus 90 here, can you see?
Yes, sir.
Yes? There? To plus 40, coming back to minus 90, going to about minus 94, and then coming back to minus 90. That's the action potential. Are we okay?
Yes.
Let's look at what happens with the sodium and the potassium conductance. Now I look at the bottom graph. Okay? See sodium? Can you see sodium?
Yeah.
Yes? Look at sodium. So during this part of the action potential, see how quickly sodium goes up. Because it's quick. It's a rapid entry. Okay? The minute the sodium channel closes up on the top, it quickly slows down as well. It's within. Okay? Within 0.5 milliseconds, it's open and closed. But look at the potassium conductance. Look at the potassium conductance. Can you see it? It goes up slowly, slowly, slowly. And then it goes slowly down again. And this is why you have a hyperpolarization. Can you see? You're still having potassium conductance at this stage. All right? And if you take the ratio of sodium to potassium conductance, you get this black graph. So there's your hyperpolarization, there's your potassium conductance. And this would be the ratio of sodium to potassium conductance. Again, in the upstroke, it's because of the sodium permeability. In the downstroke, it is because the sodium permeability decreases and the potassium permeability increases. In the hyperpolarization, is because the potassium conductance carries on because of the delay in closing the potassium channel. Okay? Next one. Now, there is a time in the action potential, all right, when it doesn't matter how much more extra voltage you put in, the channel will not open. That is called the absolute refractory period. Why? Because the sodium channel is inactivated. Okay? Because you inactivated the sodium. Remember, I need the sodium channel for the upstroke. And the only way to open the sodium channel is to either have it in a closed state or in a in an opening state. It hasn't quite opened, but it's opening. All right? So, if the sodium channel is inactivated, the sodium will not move from outside to inside. And that is called the absolute refractory period. Then you have a time that's called the relative refractory period, where, remember the ball?
Yeah.
The ball is like kind of moving away. It hasn't quite moved away, it is moving away. In other words, I'm close to resting membrane and the ball is slowly moving away. If I give it a big voltage, then that will push the ball away, and now I will be able to open the channel. And that would be called the relative refractory period. And if you have a look at that, can you see this pinkish thing here? Can you see this pinkish thing?
Yeah.
Yes?
Yes.
See this time here? Yes, no?
Yes. Yes.
That would be, if you see up here, it will tell you absolute refractory period. In other words, from that time that the voltage-gated sodium channel opened, okay, till resting, coming back to resting membrane again, all of that time is absolute refractory period. Okay? It's approximately 1 millisecond or 1.5 milliseconds. Now, from here onwards, we call that the relative refractory period, where this little ball kind of thing, can you see what's happening? Can you see the ball is shut? It's shut. Here it is also shut. But what's starting to happen is the ball is starting to move away. Can you see?
Yes.
Now if I use a big voltage, I can push the ball away, or I can open the inactivation gate and allow the sodium to go in. All right? And that will give me another action potential. And therefore, that would be called the relative refractory period. So, are there any other ions involved in the action potential? Well, the ions that are not moving, the negative ions, or the protein negative ions on the inside, they are called the non-permeant ions, the negative ions. Keep in mind that the negative or the impermeable ions will create the opposite charge inside a cell, and that will hold on to the positive charges. So yes, they play a role. Don't forget them, is what I'm getting at. What about our friend calcium? Where is the calcium more?
Outside.
Outside the cell compared to inside the cell?
Outside.
Outside the cell. Well, calcium actually helps in regulating the opening of the sodium channel. Because when you have normal calcium, it sits outside the sodium channel, okay, it sits there and it waits until the voltage reaches threshold. When it reaches threshold, then the calcium is kicked out and then the sodium comes in. Now ask yourself a question. What happens if somebody has hypocalcemia? Lower than normal extracellular calcium. What would you expect? Yes, sir? Huh? Yes?
More sodium goes inside.
Because this thing is not outside. All right? And therefore, you will not have that regulation of the sodium channel. That means in hypocalcemia, you will have hyperexcitability. Okay? So that's why in people who have hypocalcemia or low extracellular calcium, you have tetany. In other words, contraction, because the sodium channel is kind of remaining open. Again, calcium ions, just to remind you, is pumped using a calcium ATPase into sarcoplasmic reticulum, endoplasmic reticulum, or pumped out of the cell so that you remain at low concentrations inside the cell all the time. Can calcium be used in the action potential? Yes, it can. Okay? And again, we have a high calcium outside compared to inside. There are these what we call voltage-gated calcium channels that allow both calcium and sodium to enter. Where do you find these kinds of channels? You find them in the heart and in smooth muscle. In cardiac muscle and in smooth muscle. Okay? And because these are slow channels, calcium and sodium enter, they enter slowly. That's why you can have a long contraction in smooth muscle. Threshold, again, is that place where you need to come. It's approximately 15 to 20 millivolts from the resting membrane potential. You need to come to that point to allow the voltage-gated sodium channels to open. That's when the sodium influx will exceed the potassium efflux, or moving out. Okay? If you have a stimulus or voltage less than the threshold, that's called subthreshold, and therefore you may not generate an action potential. Okay? Again, when the action potential is generated, in other words, above threshold, you have an or none. Some action potentials are different. For example, look at the cardiac muscle potential. Here, potassium is regulating the resting membrane. Sodium is regulating the depolarization. Who regulates this bit? Calcium. The slow calcium channel will regulate this top bit. Okay? And then potassium kicks back in to bring about repolarization. Now, why do I need this kind of plateau in, say, a cardiac or a smooth muscle? So I can have a sustained contraction. Okay? Again, this is due to the slow calcium-sodium channels that are found in the membrane. You then have another kind of action potential. And this one does not depend on a stimulus. In other words, it naturally decays. So look, I have an action potential going up, come down, and then it naturally goes up towards the threshold. All right? And this will be found like in the SA node, cyanoatrial node. Or it will be found in the part of the brain that regulates our breathing, in the brainstem. So you constantly fire every time you need a breath, or you need a heartbeat. Okay? So for spontaneous rhythmicity, all right, the channel is the slow sodium or calcium-sodium channel. When it reaches resting membrane, the sodium keeps going in, and then it decays up to threshold, and now you fire with the voltage-gated sodium channel. Okay? And that's what I'm telling you here. Now, these action potentials, I told you, give information. How does it give information? If it is the same height, you do not have a small or a big action potential. If it is the same height or amplitude all the time, the only way you can encode information in an action potential, it has a constant amplitude, yes? Is by looking at the frequency. Can you see the frequency? All right? So if the action potential is coming fast, or it's coming slowly. 1, 2, 3. That's how you code information, by the frequency of the action potential. Okay? So, action potentials are all or none, initiated by depolarization, constant amplitude. They also have a constant velocity. So if you're looking at a nerve, say, a non-myelinated nerve, can you see a red? You look at this one, 400 to 800 micrometers. Notice the velocity is only between 0 and about 10 meters per second for non-myelinated. So it's very slow. Myelinated nerves, now look. Myelinated nerves, velocity can range from about 15 all the way up to 75 meters per second. That's very fast. Okay? How do you study these voltage changes? In terms of the squid axon, you just needed a electrode, you put it into the axon. In this case, you can study the actual channel. Now you need this pipette kind of thing. You put it on a membrane, you put a little slight pressure on the pipette, it will pull the channel on the end of the membrane. And now you can use that to study. This is called patch clamping. Okay? Good. You can watch this in your own time.
What is